Last time on Exhibition Chemistry, we were left with some unfinished business. We were able to get as much nuance as was needed from a neutralisation reaction to help students visualise the ionic equation in action, following the disappearing ions with a conductivity probe. Today, we're going to do a deep dive on strong and weak acids and see just how much a conductivity graph can reveal to us about the makeup of solutions at different stages of the reaction. Now, if you're coming to this video without having seen part 1 in last month's column, you really need to go there first. I explain in detail why I've chosen the concentrations that I have, and much of that won't be repeated in detail here. I'm going to assume that you're up to speed with the basic setup, the choice of equipment, and the logic of the dilutions that I've used. We looked at sulfuric acid reacting with barium sulfate, and we precipitated out the spectator ions to hone in on the H++ OH- makes neutral H2O aspect of the reaction. I apologized in advance for talking about acidic solutions as containing hydrogen ions, so now let's apply a little bit more complexity and nuance for an older audience. I'm going to repeat the setup here with a solution of 0.1 molar hydrochloric acid. Don't forget the important dilution step. The first thing to point out is the brightness of the bulb. Our acid is fully dissociating in solution. The conductivity is high. This time, instead of adding barium hydroxide, we'll track the far more common sodium hydroxide titration. Opening the tap all of the way is fine this time because we don't need to wait for the precipitation to complete as we did before. In this early part of the titration, a pH curve will barely budge, but by tracking conductivity without those logarithmic effects, we get an immediate and linear drop. This time, we won't get to zero, as there are sodium ions and chloride ions remaining in solution. Just like before, as we add more sodium hydroxide to the neutralized solution, the conductivity rises once more, but not at the same rate. We saw this in the barium hydroxide titration. Before we talk about gradients, though, there's a more immediate question that we ought to be asking ourselves. Why is the conductivity dropping at all? I mean, we're starting with a solution of positive and negative ions from the hydrochloric acid. At the equivalence point, we have a solution of positive and negative ions from the sodium chloride. The chloride ions remain in solution, while the hydrogen ions are replaced, as they neutralize out, 1-to-1 with the sodium ions. The trick is, of course, that there aren't naked hydrogen ions in solution at all. Last time we parked this hydronium problem, and now it's time to revisit it. When a potential difference is applied across solutions of aqueous ions like sodium or chloride, the whole ion needs to drag itself through the solution, commonly bringing with it a hydration shell which adds significantly to the bulk. We saw in the movement of ions demo from November 21 that this bulk motion is deceptively slow. But acids don't form hydrogen ions in solutions divorced from the surrounding water molecules. Rather, they form hydronium ions, the conjugate acid of water. Instead of the whole ion moving around, the extremely labile hydrogen ions hop from one water molecule to another, allowing for a vastly superior conductivity than other ions. In the same way, hydroxide ions could be thought of as the mirrors of this process, hydrolyzing neighboring water molecules so that an absence of a proton hops through the solution. So, solutions containing hydronium or hydroxide ions will conduct much better than other ions of the same charge, leading to the decrease towards the equivalence point. The spectator ions themselves will contribute in different ways to the gradient, as even for ions of similar charge, differences in size will impact the hydration shell and lead to corresponding differences in the gradient of the lines, coming into and out from the equivalence point. This was particularly noticeable in the titration that we did last time. Just one curve here has hugely developed the model that we have for the behavior of the particles in solution from this simple titration. But post-16 courses, and even some 14 to 16 courses, will also require that students differentiate between strong and weak acids in terms of their degrees of ionization or dissociation in solution. So let's see if we can see those differences reflected in our conductivity. I've set up the same titration as before, but this time with 0.1 molar ethanoic acid. If you concentrate on the timing, you can compare both lines on the same axis. But distracted by the filming process, I didn't perfectly time it here. But it's good enough to see what we want to see. The first thing to point out is the dim light on the conductivity tester at the start. The value of the conductivity of the solution is correspondingly much smaller for the same concentration as it was with the strong acid. If you're doing pH curves, your students might expect an initial jump up in pH as a strong base is added to a weak acid. Here we see a drop in the highly conductive hydronium ions reflected in a drop in conductivity, but the graph is much more shallow and quickly switches to a positive gradient. The drop in the already low concentration of hydronium ions is now being more than compensated for by not only the addition of the sodium ions, which we had last time, but by locking in the ethanoate ions, which originally would have been overwhelmingly floating around, associated in solution with the hydrogen of the carboxyl group attached. The conductivity rises to the equivalence point where, once we run out of acid to mop up the added hydroxide ions, the conductivity rises more rapidly for the reasons explained before. Notice how the gradients of the lines after the equivalence point match each other so beautifully, demonstrating the equivalent role of the hydroxide ion in the solution. There's a weird cognitive trap waiting that I might suggest you probe with your students if doing this. What do you think is going to happen to the conductivity of the solution now if we add some more acid to it, neutralizing the excess sodium hydroxide? Let's give it a try with the undiluted ethanoic acid. Your gut instinct and that of your students might be to think, well, the conductivity will go down again. But of course, all we're doing is making more ions. The conductivity is going to continue, in fact, to rise, just not as steeply as it did before. So this is where I pull everything together and show you the pièce de résistance. Just like I mentioned in the previous video, you can, with a bit more patience and probably the input of some student-led inquiry rather than as a demonstration, collect data against volume rather than against time. Applying a volume correction to the conductivity values, you can get these curves for the three reactions that we've looked at. These data were collected with concentrations 10 times less than those outlined before, as I have the resolution for it with my conductivity probe. Okay, it makes for an easier cleanup, and I also benefit from minimizing ion-ion effects that cause conductivity to change in a non-linear fashion as you go to higher concentrations. Notice the way that the sulfuric acid is almost twice the conductivity of the monoprotic HCl, which is in turn 10 times more conductive than the weak acid. This is from a rough titration at home over the holidays with bench solutions using cheap jewelry balances, thanks Bob Worley, for gravimetric dilutions, and I still had beautiful trend lines crossing within a couple of microsiemens per centimeter of the conductivity of my deionized water alone, and really close to the halfway point of the burette. One of my favorite Bob Worleyisms is the phrase, "In a little, you can see a lot." I was sick to death of titrations by the time I finished my second year of uni. Who would have thought 20 years later I would be geeking out over them? I found the journey to this graph deeply satisfying, so I hope that some of you might feel the same way and use it to stimulate some cool discussions with your classes too.